Hello, in this lecture we'll answer two questions. In the first question, we'll find out the radius of this circle that is inscribed by the right triangle ABC. And in the second question, we'll find out the area of the blue right triangle DCB that is inscribed by the quarter circle. So we'll start with the first question. In the drawing, we have the right triangle ABC. We know that side AB equals to 8 units. We also know that angle ABC equals to 90 degrees. And the length of side BC and the hypotenuse AC, their lengths are integers. And we want to find out the radius of this circle that is inscribed by the right triangle ABC. So first of all, we will define the side BC as A, and we will define side AC as B. Okay. In the next step, we will implement the Pythagoras theorem on the right triangle ABC. According to the Pythagoras theorem, the right triangle ABC by PT is a expression for Pythagoras theorem. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, the hypotenuse is AC, therefore the square of the hypotenuse is AC squared. And it is equal to the sum of the squares of the perpendiculars. That is to say, it is equal to AB squared plus BC squared. Repeat again, in the right triangle ABC, according to the Pythagoras theorem, AC squared equals to AB squared plus BC squared. Okay, so AC equals to B according to our definition, therefore AC squared is B squared. It is equal to AB squared. AB equals to 8, so AB squared is 8 squared, that is 64, plus BC squared. BC equals to A according to our definition, therefore BC squared will be equal to A squared. So in conclusion, according to equation number 1, we found out that B squared equals to 64 plus A squared. We subtract A squared from this equation number 1, and we will get that according to equation number 1, B squared minus A squared equals to 64 Here we will use the algebraic identity that B squared minus A squared equals to B plus A times b minus a, so we substituted b squared minus a squared by b plus a times b minus a, and according to equation number 1, it is equal to 64. So actually, according to what is given as the question, a, c, and bc are integers, but ac equals to b and bc equals to a, so we can write down that a and b are integer according to what is given as the question. A and b are integers. This is the first thing that you can write down, that a and b are integer, and the second thing is that a and b are the lengths of the hypotenuse and the perpendicular in the right triangle ABC. So a and b as lengths they must be positive numbers. So from 1 and 2 we can derive that, in conclusion, that a and b are positive integers. And so b is a positive integer and a is a positive integer, therefore b plus a must be also a positive integer. B plus a is a positive integer because when you add two positive integers to each other, the result must be also a positive integer. And because of the fact that a and b are positive integers, it means that b plus a must be greater than b minus a, because when you add two positive integers to each other, the result must be greater than the case that when you subtract them from each other. Okay, and also we know that b is the hypotenuse of the right triangle ABC. Therefore, the hypotenuse b is always will be greater than the perpendicular a. So b is greater than a. We subtract a from this inequality and we get that b minus a is greater than 0. So we know that b is a positive integer, a is a positive integer, and b minus a is a positive number. So if b minus a is a positive number, it must be a positive integer. Why? Because when you subtract two positive integers from each other, the result must be a positive integer. If the result is positive, then it must be a positive integer. Okay, so in conclusion, we found out that b plus a is a positive integer, b minus a is also a positive integer, and b plus a is greater than b minus a. Okay. So actually, according to question number 1, b plus a times b minus a equals to 64. It means that when we multiply two positive integers by each other, the result is 64. Now we will write down all the possibilities that we have to multiply two positive integers by each other, and the result will be 64. Actually, there are not a lot of possibilities, so we write down all the possibilities for two positive integers that we will multiply one by each other, and the result will give us 64. So here, actually, the first possibility is that b plus a equals to 1 and b minus a equals to 64. The second possibility is b plus a equals to 2 and b minus a equals to 32. The first possibility is b plus a equals to 4 and b minus a equals to 16. The fourth possibility is that b plus a equals to 8 and b minus a also equals to 8. The fifth possibility is that b plus a equals to 16, while b minus a will be equal to 4. And the sixth possibility is that b plus a equals to 32 and b minus a equals to 2. And the last possibility is that b plus a equals to 64 while b minus a equals to 1. Okay, so we have in total 7 possibilities that we can take two positive numbers and the multiplication of them will give us 64. Okay, but because of the fact that b plus a is greater than b minus a, it means that the first column, that is b plus a, must be greater than the second column, that is b minus a. So that is to say, we take only the options where the first column is greater than the second column. So the possibility in the first column is greater than the possibility in the second column. So here 1 is not greater than 64. That is to say, it is not a good option because b plus a must be greater than b minus a. 2 is not greater than 32. That is to say, it is not a good option. 4 is not greater than 16. It is not also a good option. 8 is not greater than 8. That is to say, it is not a good option. Here 16 is greater than 4. 16 is greater than 4, therefore it is a good possibility. Because b plus a is greater than b minus a. 32 is also greater than 2. It is also a good option. And finally 64, it is also greater than 1, so it is also a good option. So only 3 options are left here for the values of b plus a and b minus a. In the next step, we will add the two numbers together. We will add b plus a to b minus a in order to find the result, and we will conclude from the result which more options we can cancel. So b plus a plus b minus a is b plus b is 2b, and a plus minus a is a minus a, that is 0. So in conclusion, we found out that if we add the two numbers together, the result must be 2b, that is an even number. B is a positive integer, therefore 2b must be an even number. So now we will cancel all the possibilities, but that will not give us an even number. That is to say, if we add the two numbers together and the result is not an even number, we'll cancel this option. So here 16 plus 4 is 20, and 20 is an even number. That is to say, it is a good option. 32 plus 2 is 34. 34 is also an even number, so it is also a good option. And finally, 64 plus 1 is 65. 65 is not an even number, so we cancel this option. So we left only two possible options for b plus a and b minus a. So either b plus a equals to 16 and b minus a equals to 4. And the second option is that b plus a equals to 32 and b minus a equals to 2. So here I will write down all the two options that left for b plus a and b minus a, and we will find out the values of a and b themselves. So here, according to the second option, according to the first option, b plus a equals to 16. While b minus a equals to 2. And according to the second option, b plus a equals to 32. And b minus a equals to 2. Okay, so we have here two options. We will focus on the first option, and so in the next step we will find out the values of a and b. We will focus in the first option here, and here b minus a is 4. So we will focus on the first option, that b plus a equals to 16 and b minus a equals to 4. We will add equation number 1 to equation number 2, and we get that b plus b is 2b, a plus minus a is a minus a, that is 0. In the other side of the equation we have 16 plus 4 is 20. So in conclusion, we found out that 2b equals to 20. We divide this equation by 2, and we get that b equals to 20 over 2 is 10. So b equals to 10 units. And here we have this equation that b plus a equals to 16. Here we will subtract b from this equation, and we will get that a equals to 16 minus b. So a equals to 16 and b is 10, so it is 16 minus 10, that is 6. So in conclusion, according to the first option, we found out the values of a and b. That is to say, a equals to 6 units, and B equals to 10 units. Okay, and then next step we find out the second option for A and B. So we will add equation number 1 to equation number 2 here, and we will get that B plus B is 2B. A plus minus A is A minus A, that is 0. And in the other side of the equation we have 32 plus 2, that is 34. Here we divide this equation by 2, and we get that B equals to 34 over 2 is 17, and according to the first equation, B plus A is 32. So we subtract B from this equation, and we get that A equals to 32 minus B. So A equals to 32 and B is 17, so it is 32 minus 17, so 32 minus 17 is 15. So in conclusion, we found out that according to the second option, A equals to 15, and the hypotenuse B equals to 17. So I will draw the two possibilities for the solution to the question here. So actually we have a right triangle, triangle ABC. In the right triangle, triangle ABC, it is given us in the question that side AB equals to 8 units, angle ABC equals to 90 degrees. According to our definition, BC equals to A, and A equals to 6 units. And according to our definition, AC equals to B, and B equals to 10 units. Inside this right triangle, we have a circle that is inscribed by the right triangle. This is the circle that is inscribed by this right triangle. And our mission is to find out the radius of this circle. So we define the radius of this circle as R, and our mission is to find out the value of R, the radius of this circle. So this is the first option, and according to the second option, we have another right triangle, triangle ABC. Again, ABC equals to 90 degrees, side AB equals to 8 units according to what is given as the question. BC is A, and A according to the second option is 15 units, and AC according to our definition equals to B, and B, the hypotenuse B equals to 17 units. Inside this right triangle, we have a circle that is described by the right triangle, triangle ABC. And actually, our mission is to find out the radius of this circle. Okay, so we define the radius of this circle as capital R, and our mission is to find out the radius of this circle. Okay, so we have two options two options for the solution of the question. There are two possibilities for the right triangle that we have here. In each triangle we have a circle that is inscribed by this right triangle, and we want to find out the radii of the two circles that are inscribed by those two right triangles. So actually, in order to find out the radius on the radii of those two circles, we'll take triangle ABC that is a right triangle. So here, triangle ABC could be any right triangle, and we will find out the radius of this circle that is inscribed by this right triangle, triangle ABC, that could be any right triangle. And after we find out the radius of this circle that is inscribed by this right triangle, we'll use the formula that we will get here in order to find out the radii of those two specific right triangles. Okay, so here we define, our mission now is to find out the radius of this circle that is inscribed by the right triangle, triangle ABC, that could be any right triangle. So first of all, we define side AB as A. That is to say, side AB equals to A units. According to our definition, we define side BC as B. That is to say, side BC equals to B units according to our definition. And we define the hypotenuse AC as C. That is to say, the hypotenuse AC equals to C according to our definition. Okay. We define the center of this circle as O. We define the point of tendency of tangent AC with this circle as L. We define the point of tendency of tangent BC with this circle as point N. And we define the point of tendency of tangent AB with this circle as M. In the next step, we will join points O and M together by a straight line. So what is the definition of line segment OM? Actually, here we know that point O is the center of the circle. Point M is the point of the circle itself. This is exactly the definition of a radius. That is to say, OM, line segment OM, is the radius of this circle that is equal to capital R. Okay. Here we have rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. That is to say, here we have the radius OM that is drawn to the point of tendency. That is to say, it is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever we have a radius that is drawn to the point of tendency, then according to rule number 1, tangent AB will be perpendicular to the radius MO. So if AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle will also equal to 90 degrees according to rule number 1. Likewise, we have here the radius ON that is drawn to the point of tendency. That is to say, it is drawn to point N, that is the point of tendency of tangent DC with this circle, and whenever we have a radius that is known to the point of tendency, then according to rule number 1, tangent BC will be perpendicular to the radius NO. So if BC is perpendicular to NO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees. So actually in quadrilateral MOBN, we have 1, 2, 3 right angles, and the sum of 3 right angles is 90 times 3 is 270 degrees, plus the size of the fourth angle, that is actually angle MON. In total, the sum of those 4 angles must be equal to 360 degrees. So 270 degrees plus the size of angle MON must be equal to 360 degrees. According to the rule, the sum of the angles in any quadrilateral is equal to 360 degrees. We subtract 270 degrees from the equation, and we will find out that the missing angle MON equals to 90 degrees. So angle MON equals to 90 degrees, it is a right angle. So inside quadrilateral MOBN, we have 4 right angles. And any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate to quadrilateral MOBN as a rectangle, and we know that the opposite sides of rectangle are equal to each other. So rectangle MOBN, MO equals to BN. MO equals to BN from one side, but we know that MO equals to R from the other side. Okay? Therefore, we'll conclude from it that BN is also equals to R. Okay? Likewise, according to the rule that the opposite sides of rectangle are equal to each other, we will get that MB equals to ON. MB equals to ON, but we already found out that ON equals to R, and ON equals also to BM. So from that we can conclude that MB is also equals to R. So actually we found out that quadrilateral MOBN, it is not a rectangle but a square, because all of its sides are equal to each other, they are equal to R. So we find out the length of line segment NC from the drawing. It is very easy to see that NC equals to BC minus NB. Again, BC minus NB equals to NC. So NC equals to BC, that is B according to our definition, minus BN, that is R. So in conclusion, line segment NC equals to B minus R. Likewise, we find out the length of line segment AM. AM, from the drawing, it is very easy to see that AM equals to AB minus MA. So AM equals to AB, that is A minus BM, that is R. So in conclusion, we found out that AM equals to A minus R, while NC equals to B minus R. Okay, in the next step I will present to you rule number 2. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. I repeat again, the lengths of two tangents from a common external point to a circle are equal. So if we focus on the common external point, point A, from the common external point A, we have two tangents to this circle, tangent AM and tangent AL. And according to rule number 2, they are equal to each other. That is to say, AM equals to AL according to rule number 2. So AM equals to AL according to rule number 2 from one side, but we already found out that AM equals to A minus R. Okay? And AM also equals to AL, therefore AL must be also equal to A minus R. Okay? Likewise, if we focus on the common external point, point C, from the common external point C, we have two tangents to this circle, tangent CL and tangent CN. And according to rule number 2, they are equal to each other. That is to say, CL equals to CN, according to rule number 2. But we have already found out that CN equals to B minus R. therefore CL must be also equal to B minus R because they are equal to each other. So in conclusion, we found out that CL equals to B minus R and AN equals to A minus R. So what is the length of the hypotenuse AC? From the drawing, it is very easy to see that AC equals to AL plus LC. I'll repeat again. The hypotenuse AC equals to AL plus LC from the drawing. You can see it. According to our definition, AC equals to C, so we'll substitute AC by C. And for the drawing, it is very easy to see that AL equals to A minus R, so we'll substitute AL by A minus R. And LC equals to B minus R, so we'll substitute LC by B minus R. And in conclusion, we found out that C equals to A minus R plus B minus R. That is to say, C equals to A plus B minus R is minus 2R. So C equals to A plus B minus 2R. Here we'll add 2R to this equation and we'll get that R plus C equals to A plus B. Here we'll subtract C from this equation and we'll get that 2R equals to A plus B minus C. So here we'll divide this equation by 2 and finally we get the radius that we are looking for. R, the radius of the circle that is described by the right triangle ABC, that could be any right triangle, it is equal to A plus B minus C over 2. Okay, so the radius of the circle that is described by the right triangle ABC, that could be any right triangle, it is equal to A plus B, that is actually the sum of the perpendiculars in the right triangle ABC minus C, that is minus the hypotenuse C over 2. And because of the fact that the right triangle ABC could be any right triangle, we can use this formula that we found for our two specific right triangles. So our two right triangles, so write down the formula that we found here, that R equals to A plus B, that is the sum of the perpendiculars, minus C, that is minus the hypotenuse, over 2. And we find out the radius of those two circles that are described by those two right triangles. Okay, so here R equals to A plus B is 8 plus 6, minus C, minus the hypotenuse C, that is 10 over 2. So 8 plus 6 is 14, and 14 minus 10 is 4, and 4 over 2 is 2. So in conclusion, I found out that the radius of this circle that is described by this triangle ABC, by this right triangle ABC, equals to 2 units. This is the first solution to the question. And here we find out the second radius that is described by this right triangle ABC. Here R will be equal to A plus B, that is the sum of the perpendiculars, 8 plus 15, minus the hypotenuse, that is 17 over 2. So 8 plus 15 is 23, and 23 minus 17 over 2, 23 minus 17 is 6, and 6 over 2 is 3. So we found out that the radius of this circle that is described by this specific right triangle ABC equals to 3 units. So R equals to 3 units. So In conclusion, we have two solutions to the question. The radius of this specific circle that is described by this right triangle ABC could be equal to either 2 units or 3 units. Okay, I write the answer here that the radius of the circle that is described by this specific right triangle ABC could be equal to either 2 units or 3 units. Okay, and that is the answer to the question. So we finished with the first question. In the next step I will present to you the second question, and we will solve the second question in two different methods. So in the drawing we have a quarter circle. AOB is a quarter circle. Side OB equals to 2 units. We also know that AD equals to DO. And we want to find out the area of the blue right triangle, triangle DCB. We'll start with the first method. First of all, because of the fact that AOB is a quarter circle, it means that angle AOB equals to 90 degrees. This is the first thing. And also, you can conclude from it that point O is the center of the quarter circle. And the radius of this quarter circle is OB, that is equal to also AO, that is equal to 2 units. So you can write down that the radius of the quarter circle equals to AO, and from the drawing it is very easy to see that AO equals to AD plus DO, and it is also equals to OB. It is the radius of the quarter circle, and according to what is given as the question, it is equal to 2 units. So if we define the length of AD as x, then DO must be also equal to x because they are equal to each other. Okay? So here AD equals to x and DO also equals to x according to our definition. So from this long equation we have x plus x is 2x, and 2x equals to 2 according to this long equation. 2x equals to 2. We'll divide this equation by 2 and we get that x equals to 1. Okay, so we found out that x equals to 1 unit. So you can write down here that x equals to 1 unit. Here x equals to 1 unit. AD that is equal to x equals to 1 unit. And DO that is also equals to x, it is equal to 1 unit. Okay? So in the next step, we'll complete the quarter circle to a circle. So we completed the quarter circle to a circle, and we will extend the radius OB by a straight line until it touches the circle, and we will define the touching point of the extended radius BO in the circle as point P. Here point O is the center of the circle, point P is the point on the circle itself, therefore PO is the radius of this circle that is equal to 2 units, because the radius of the circle is the same as the radius of the quarter circle, that is to say it is equal to 2 units. So actually we extended the radius BO by a straight line, so when you extend a straight line by straight line, you will get a straight line, so BP is a straight line, and the straight line BP, you can define it also as chord BP, and we have chord BP that passes through the center of the circle, and any chord that passes through the center of the circle is defined as the diameter of the circle. So BP is the diameter of the circle, so we know that BP is the diameter of the circle, and in the next step we will extend side CD by a straight line until it touches the circle, and because we don't know where the extended side CD will touch the circle, we will assume that the extended line segment CD or side CD will touch the circle at point X. This is point X, that is the touching point of the extended side CD with this circle. Okay? Our assumption is the extended side CD will touch the circle at point X. So actually we created here peripheral angle BCX. Here peripheral angle BCX. BCX is the peripheral angle because of the fact that it touches the circle at 3 points. At point B, at point X, and at point C, that is the vertex of the angle, the peripheral angle BCX. So we created here peripheral angle BCX that is equal to 90 degrees. According to what is given as the question, this angle equals to 90 degrees. That is to say peripheral angle BCX equals to 90 degrees. Okay, so here we have peripheral angle BCX that is equal to 90 degrees, and it doesn't rest on the diameter of the circle, that is PB. But we have the rule that any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle. That is to say, peripheral angle BCX must rest on PB, that is the diameter of the circle. But peripheral angle doesn't rest on the diameter of the circle, but it rests on chord BX, that is not the diameter of the circle. So we have here contradiction, because this peripheral angle BCX that is equal to 90 degrees must rest on the diameter of the circle, that is PB. So in order to solve the contradiction, we'll conclude that point X must merge with point P, and then when point X merge with point P, we'll get here peripheral angle BCP and peripheral angle BCP indeed rests on the diameter of the circle, that is PB. Otherwise, we will arrive to the contradiction that we will have a peripheral angle that it doesn't rest on the diameter. So in order to avoid the contradiction, we must conclude that point X merges with point B, and we have here peripheral angle BCP, that it is equal to 90 degrees, and it rests on the diameter of the circle that is PB. So we conclude that any peripheral angle BCX that is equal to 90 degrees, it is actually equals to peripheral angle BCP, that is to say, point X merge with point P, and here we have the peripheral angle BCP that it is indeed rests on the diameter of the circle that is PB. Okay? So that is to say, we can conclude from it that when we extend side CD by a straight line, it must touch the circle at point P and only at point P, otherwise we'll get to a contradiction here. Okay? So we know that BP is the diameter of the circle, and as a diameter it must be, BP must be a straight line, so we know that PB is a straight line, and we have the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So we have here the straight line PB. So if we focus on the upper side of the straight line PB at point O, here the sum of the angles must be equal to 180 degrees. So we have here 90 degrees plus the size of this angle that is actually angle AOP. In total, they must be equal to 180 degrees according to the rule that I mentioned. So if we subtract 90 degrees from this equation, we will get that the missing angle AOP equals to 90 degrees. Okay? So in the next step, we will focus on the right triangle PDO, this right triangle. In the right triangle PDO, by PT is a relation for Pythagoras theorem. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, PD square equals to DO square plus PO square. I repeat again, in the right triangle PDO, PD square equals to DO square plus PO square according to the Pythagoras theorem. So PD square, the square of the hypotenuse, equals to DO square. DO is 1, so DO square is 1 square, that is 1, plus PO square. PO is 2, therefore PO square is 2 squared, that is 4. Okay, so in conclusion, we found out that PD square equals to 1 plus 4, that is 5. Here we take out of this equation and we will get that PD, the hypotenuse PD, equals to the square root of 5 units. Okay, so we found out that the hypotenuse PD, this hypotenuse PD equals to the square root of 5 units. We will repeat on the same process on the right triangle DOB, this right triangle. So according to the Pythagoras theorem on the right triangle DOB, by PT, dB square equals to DO square plus OB square. Repeat again, in the right triangle DOB, according to the Pythagoras theorem, dB square equals to DO square plus OB square, so dB square equals to DO is 1, so DO square is 1 squared, that is 1, plus OB square. OB is 2, so OB square is 2 squared, that is 4. So in conclusion, we found out that dB square equals to 1 plus 4, that is 5. Here we take out all of this equation, and we will get that dB equals to the square root of 5 units. So we found out that dB is also equals to, the equation of dB also equals to the square root of 5 units. Okay, so in the next step, we'll extend the radius AO by a straight line until it touches the circle at this point, point Z. So the touching point of the extended radius AO in the circle is at point Z. In the next step, I will present to you rule number 1, and we will implement rule number 1 in our drawing. Rule number 1 deals with two chords that intersect with each other inside a chord. I've already mentioned this rule a couple of times in the past. So repeat on it quickly, and we'll implement the rule in our drawing. Okay, so according to rule number 1, if we have here a circle, and we also have chord AB. Here we have chord AB. This is chord AB. That intersects with chord CD. This is chord CD. And the intersection point is at point O. So if chord AB intersects with chord CD at point O, then the following equation is true, that AO times OB equals to CO times OD. I repeat again. If chord AB intersects with chord CD at point O, then AO times OB equals to CO times OD. Okay? So we actually can implement rule number 1 in our drawing, because in our drawing we have chord AZ. This is chord AZ that intersects with chord CP at point D. Write it down. Chord AZ intersects with chord CP at point D. Therefore, according to rule number 1, AD times DZ equals to CD times DP. Again, AD times DZ equals to CD times DP. Repeat again, according to rule number 1, AD times DZ equals to CD times DP. Here, what is the length of line segment OZ? The length of line segment OZ is, we know that O is the center of the circle, Z is the point on the circle itself, therefore OZ is the radius of this circle, that is equal to 2 units. So here AD AD equals to 1 unit. DZ, for the drawing it is very easy to see that DZ equals to 1 plus 2, that is 3. And it is equals to CD. CD is the missing segment, so we leave it as it is. Times DP. DP equals to square root of 5 units. So in conclusion, I found out that 3 equals to CD times square root of 5 units. Okay, 3 equals to square root of 5 units times CD. Here we divide this equation by square root of 5, and we get that CD equals to 3 over square root of 5 units. CD equals to 3 over square root of 5 units. So CD equals to 3 over square root of 5 units. In the next step, we will implement the Pythagoras theorem on the right blue triangle, triangle CDB. Okay, so in the right blue triangle, triangle CDB, by PT, the square of the hypotenuse equals to the sum of the squares of the perpendiculars, that is to say, DB squared equals to DC squared plus CB squared. I'll repeat again. According to the Pythagoras theorem on the right triangle, the right blue triangle, triangle CDB, DB squared equals to CD squared plus CB squared. So DB equals to square root of 5, so DB squared is square root of 5 squared, that is 5. And it is equal to CD squared. CD squared, CD is 3 over 5, 3 over square root of 5 units, so CD squared is 9 over 5. CD squared is 9 over 5. Plus CB squared is the missing sign, so we leave it as it is. So we have 5 plus 5 equals to 9/5 plus CB squared. We subtract 9/5 from this equation and we get that CB squared equals to 5 minus 9/5. Here we multiply 5 by 5 and then we divide it by 5 in order to have a common factor with this expression, and we get that CB squared equals to 5 times 5 is 25, so it is 25 minus 9 over 5. Here, so CB squared equals to 25 minus 9 is 16, so we have 16 over 5, that is equal to CB squared. We take a root out of this equation and we get that CB equals to the square root of 16 is 4 over square root of 5. So in conclusion, we found out that CB equals to 4 over square root of 5 units. Now it is very easy to find out the area of the blue shape. It will be equal to the base of the triangle, that is CD, times the height to the base, that is CB, over 2. I'll repeat again, the area of the blue right triangle, triangle DCB will be equal to the base of the triangle, that is CD, times the height to the base, that is CB, over 2. So actually, it is equal to the base, that is CD. CD is 3 over square root of 5, times the height to the base, that is 4 over square root of 5, all divided by 2. So here we got that in the numerator we have 3 times 4 is 12. In the denominator we have square root of 5 times square root of 5, that is 5, times 2. Here 12 over 2 is 6, so in the numerator we have 6 left only, and the denominator of what is left is 5. So in conclusion, we found out that the area of the blue right triangle DCB equals to either 6 over 5 square units, or in terms of numbers it is equal to 1.2 square units. Okay? So we finished in the first method. In the next step I will present to you how to find out the area of this blue right triangle DCB according to the second method. Okay? In the second method, we found the fields. We use all the fields that we only found out in the first method. Here we know that angle AOB equals to 90 degrees. It is a right angle. We know that point O is the center of the quarter circle. We have already found out that AD equals to 1 unit. DO equals to 1 unit, and the radius of this quarter circle is equal to 2 units. In the next step we will complete the quarter circle to a semicircle. So we will extend the radius BO until it touches the semicircle. At point P is the touching point of the extended radius BO and the semicircle. Point O is the center of the circle, point P is the point on the semicircle itself, that is to say PO is the radius of the semicircle that is equal to 2 units, because the radius of the semicircle is the same radius of the quarter circle. So in the next step we will extend side CD by straight line. According to the first method, when you extend side CD by straight line, it must touch the circle at point P and only at point P. Okay? And according to the first method, we have already found out that this angle is a right angle. It is equal to 90 degrees. We define angle DPO as theta. So angle DPO equals to theta according to our definition. Angle DOP equals to 90 degrees. So this angle PDO must be equal to 90 degrees minus theta in order to complete the sum of the angles in the right angle PDO to 180 degrees. This angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is 180 degrees. Likewise, in the right triangle BCP, this angle equals to theta, this angle equals to 90 degrees, so this angle must be equal to 90 degrees minus theta, again in order to complete the sum of the angles in the big right triangle to 180 degrees. This angle must be equal to 90 degrees minus theta. Okay? In the next step we will prove that the right triangle PDO is similar to the right big triangle PCB. So why those two right triangles are similar to each other? First of all, we know that those two angles, they are both equal to 90 degrees, therefore they are equal to each other. So angle POD, this angle, equals to this angle that is actually angle PCB, and they are both equal to 90 degrees, therefore they are equal to each other. I'll repeat again. Angle POD equals to angle PCB, and they are both equal to 90 degrees, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So angle PDO, this angle equals to this angle, this is actually angle PBC, and they are both equal to 90 degrees minus theta, therefore they are equal to each other. I repeat again, angle PDO equals to angle BBC equals to 90 degrees minus theta. And finally, this angle is a common angle that belongs to both triangles, therefore this angle equals to itself. So we can write down that angle DPO equals to itself. You can present it also as angle CPB, and it is equal to theta. So this angle equals to itself, angle DPO equals to angle CPB equals to theta. It is a common angle that belongs to both triangles. Okay, so actually we found out that all three angles of the right triangle PDO can go into all three angles of the right triangle PCB. Therefore, triangle PDO is similar, this is the sign of similar to triangle PCB according to angle similarity rule. Okay, and from the fact that the two right triangles are similar to each other, we derive that PD over PB equals to DO over CB, and it is also equals to PO over PC. And repeat again, from the fact that the two right triangles are similar to each other, we derive that PD over PB equals to DO over CB equals to PO over PC. Okay, so here we have already found out in the first method that PD equals to the square root of 5 units and DB also equals to the square root of 5 units. So here PD is square root of 5 units over PB. PB equals to 2 plus 2, that is 4. So here DO equals to 1 over CB. CB is the missing 9 segment, so we leave it as it is. And it is equal to PO. PO equals to 2 units over PC. PC equals to square root of 5 plus DC. So in conclusion, I found out that the square root of 5 over 4 equals to 1 over CB equals to 2 over square root of 5 plus DC. Here we will derive the first equation from this log equality, from this long equation. That is to say, here square root of 5 over 4 equals to 1 over CB. Here we cross multiply this equation, equation number 1, and we get that CB times square root of 5 equals to 4. Here we'll divide this equation number 1 by square root of 5, and we'll get that CB equals to 4 over square root of 5 units. CB equals to 4 over square root of 5 units. In the next step, we will implement the Pythagoras theorem on the right blue triangle DCB. On the right blue triangle DCB, according to the Pythagoras theorem, we will get that dB square equals to CB square plus DC square. In the right triangle DCB, according to the Pythagoras theorem, dB square equals to CB square plus DC square. Here, dB equals to square root of 5, so dB square is square root of 5 squared, that is 5. And it is equal to CB square. CB is 4 over square root of 5, so CB square is 16 over 5. That is equal to plus DC square. This is the missing isolate, so we will leave it as it is. So in conclusion, we found out that 5 equals to 16 fifths plus DC square. We subtract 16 fifths from this equation, and we get that 5 minus 16 fifths equals to DC square. Here we will multiply 5 by 5 and we will divide it by 5 in order to work common factor with this expression. And we get that 5 times 5 is 25 minus 16 over 5 equals to DC square. So here 25 minus 16 is 9, and 9 over 5 equals to DC square. So here we take a root out of this equation and we get that DC equals to the square root of 9, that is 3 over square root of 5. So in conclusion, we found out that DC equals to 3 over square root of 5. And the area of the blue white triangle will be equal to the base of the triangle, that is DC, times the height to the base, that is CB, over 2. I repeat again, the area of the height blue triangle DCB equals to the base of the triangle, that is DC, times the height to the base, that is CB, over 2. So here DC is 3 over square root of 5, times CB is 4 over square root of 5, all divided by 2. Okay, so here we have 3 times 4 is 12. In the numerator we have square root of 5 times square root of 5 is 5 times 2. Here 12 over 2 is 6. And the denominator what is left is only 5. So in conclusion, the area of the blue white triangle DCB will be equal to either 6 over 5 square units, or in terms of numbers it is equal to 1.2 square units. We finished with the second method. In the next step, I will summarize the lecture. We'll start with the first question. So, in the drawing, we have the right triangle ABC. We know that side AB equals to 8 units. Angle ABC equals to 90 degrees. Inside this right triangle ABC, we have this circle that is inscribed like a triangle, and we want to find out the radius of this circle. We know also that BC and AC are integers. Okay, So first of all we define side BC as A, side AC as B, and we implemented the Pythagoras theorem on the right triangle, triangle ABC. According to the Pythagoras theorem, AC squared equals to AB squared plus BC squared. Repeat again. AC squared equals to AB squared plus BC squared. AC equals to B, so AC squared is B squared. AB equals to 8, so AB squared is 8 squared, that is 64, plus BC squared. BC is 8, so BC squared equals to 8 squared. So in conclusion, found out that according to equation number 1, B squared equals to 64 plus 8 squared. We subtracted 8 squared from this equation number 1, and found out that B squared minus 8 squared equals to 64. Then we used the algebraic identity that B squared minus A squared equals to B plus A times B minus A. So we substituted B squared minus A squared by B plus A times B minus A, and according to rule number 1, according to equation number 1, this is equal to 64. So we know that AC and BC are integers, but AC equals to B and BC equals to A, so we can write down that A and B are integers, and because of the fact that A and B are the lengths of the sides of the right triangle ABC, so its lengths, there must be a positive numbers. So from 1 and 2 we derive that A and B are actually positive integers. So A is a positive integer and B is a positive integer, therefore B plus A must be also a positive integer. And we also know that B is the hypotenuse, and the hypotenuse is always greater than the perpendicular A. So B is greater than A. So if we subtract A from this inequality, we will get that B minus A is greater than 0. That is to say, B minus A is a positive number. So B is a positive integer, A is a positive integer. And if B minus A is a positive, it must be also a positive integer, because when you subtract positive integer from positive integer and the result is positive, it must be, if it is a positive, it must be a positive integer. Okay? So we actually found out that B plus A is a positive integer, and B minus A is also a positive integer. And B plus A, because B is a positive integer and A is a positive integer, it means that B plus A must be always greater than B minus A, because if you add two positive integers together, the result must be greater than the case that you subtract them from each other. So B plus A must be greater than B minus A. So actually, according to equation number 1, if we multiply B plus A times B minus A equals to 64, if we multiply two positive integers, B plus A is a positive integer, and B minus A is also a positive integer. So according to equation number 1, if we multiply two positive integers by each other, the result is 64. Then we wrote down all the possibilities for two positive integers that if we multiply them one by each other, the result will be 64. So we have here 7 options: 1 times 64, 2 times 32, 4 times 16, 8 times 8, 16 times 4, 32 times 2, and 64 times 1. We have 7 options for the multiplication of two positive integers that will give us the result of 64. But because of the fact that B plus A is greater than B minus A, it means that the first column, that is B plus A, must be greater than the second column, that is B minus A. So we'll take into account only the options that the first column is greater than the second column. So here 1 is not greater than 64, so we cancel this option. 2 is not greater than 32, therefore we cancel this option. 4 is not greater than 16, so we cancel this option. 8 is not greater than 8, so we cancel this option. And we have the option that 16 is indeed greater than 4, that is to say it is a good option. 32 is greater than 2, then it is also a good option, and 64 is also greater than 1, it is also a good option. So we have three possibilities for the solution of the question. And in the next step we will add b plus a to b minus a in order to find out if we have here more options to cancel all the options that we have here. So we added b plus a to b minus a, so b plus a plus b minus a equals 2b plus b is 2b, and a minus a is 0. So we found out that if we add the two numbers together, the result must be an even number because 2b is an even number. So now we can check and we can add the two numbers together in all of the options, and if we find that the result of adding the two numbers together is not an even number, we'll cancel that option. Here 16 plus 4 is 20, 20 is an even number, therefore it is a good option. 32 plus 2 is 34, 34 is also an even number, so this option is also a valid option. And finally 64 plus 1 is 65. 65 is not an even number, so we'll cancel this option. So we left only with two options that are possible for the solution of the question. That b plus a equals to 16 and b minus a equals to 4, that is the first option. And according to the second option, b plus a equals to 32 and b minus a equals to 2. Okay, so we'll focus on the first option. We'll add equation number 1 to equation number 2, and we get that b plus b is 2b and a minus a is 0. So in this side of the equation we have 2b, in the other side of the equation we have 16 plus 4, that is 20. So according to this equation, 2b equals to 20. We divided this equation by 2 and found out that b equals to 20 over 2 is 10. So b, the hypotenuse b equals to 10 units. Then we have the equation that b plus a equals to 16. We subtracted b from this equation and found out that a equals to 16 minus b. A equals to 16 minus b, and we already found out that b equals to 10 units, so we can substitute b by 10. And we substitute b by 10 and we get that a equals to 16 minus b, and b is 10, so it is 16 minus 10. And 16 minus 10 is 6. So in conclusion, we found out that the value of a is 6 units and the value of b is 10 units according to the first option. Then in the second option we add the two equations together. B plus b is 2b and a minus a is 0, and 32 plus 2 is 34. So according to here we got that 2b equals to 34. We divided this equation by 2 and we found out that b equals to 32 over 2, that is 17. So b equals to 17, and according to this equation, b plus a equals to 32. We subtracted b from this equation and we found out that a equals to 32 minus b. So a equals to 32 minus b, but we have already found out that b equals to 17, so we can substitute b by 17 and we get that a equals to 32 minus b, and b is 17. So a equals to 32 minus 17, that is 15. So a equals to 15 and b equals to 17 according to the second option. Then I draw the two options that we have for a plus b here. And according to the first option, we have here the right triangle ABC. Side AB equals to units, it is given as the equation, angle ABC equals to 90 degrees. Side BC equals to A according to our definition, and A equals to 6. Side AC equals to B according to our definition, and B, the hypotenuse B equals to 10. Inside this right triangle, with sides 8, 6 and 10, we have this circle that is described by the right triangle, by the specific right triangle, and our mission is to find out the radius of this circle. And according to the first option, we have here the right triangle ABC. Again, AB is equal to 8 units, it is given as the question. Angle ABC equals to 90 degrees, it is also given as the question. And according to our definition, BC equals to A and A equals to 15 according to the second option. And AC equals to B and b equals to 17 according to the second option. So in conclusion, we have these right triangles with sides 8, 15 and 17. And inside this right triangle we have this circle, and we want to find out the radius of this circle. So in order to find out the radius of the radii of the two circles that are described by those two right triangles, we will actually take a right triangle that could be any right triangle. Inside this right triangle we have this circle, and we will find out the radius of this circle, and then we can use the formula for the radius in our two right triangles. Why? Because triangle ABC could be any right triangle, and especially it could be those two right triangles that we found according to our solution. Okay, here the right triangle ABC could be any right triangle. And we will find out the radius of the circle that is described by this triangle ABC that could be any triangle. We can use the formula in order to find out the radii of the two circles in our specific two right triangles. Okay? So here we define side AB as A, side BC as B, and side AC as C. Then we define the center of the circle as point O. We define the point of tendency of tangent AB with the circle as N. We define the point of tendency of tangent BC with this circle as N. And we define the point of tendency of tangent AC with this circle as L. Then, according to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. Here we have the radius OM that is drawn to the point of tendency, and whenever we have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO, that is to say this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule number 1. Likewise, we have the radius ON that is drawn to the point of tendency, that is to say it is drawn to point N, that is the point of tendency of tangent ON, of tangent BC with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius NO. So if BC is perpendicular to NO, it means that this angle equals to 90 degrees, and this angle will also equal to 90 degrees, according to rule number 1. So actually in quadrilateral OMBN we have 1, 2, 3 right angles. The sum of 3 right angles is 90 times 3 is 270 degrees, plus the size of the fourth angle, that is actually angle MON. In total, they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So we have 270 degrees plus angle MON equals to 360 degrees. We subtracted 270 degrees from this equation, and we found out that the missing angle MON equals to 90 degrees. This angle equals to 90 degrees. So in quadrilateral MOBN we have 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to quadrilateral MOBN as a rectangle. We know that the opposite sides of a rectangle are equal to each other. That is to say, MO equals to BN. MO equals to BN, but we have already found out that MO equals to R. It is also equals to BN, therefore BN must be also equal to R. Likewise, according to the rule that the opposite sides of a rectangle are equal to each other, we get that MB equals to ON. MB equals to ON from one side, but we have already found out that MB equals to R, and it is also equals to ON. Therefore, you can conclude from it that ON is also equals to R. So actually found out that that quadrilateral MOBN, it is not a rectangle but a square, because all of its sides are equal to each other, they are equal to R. Then we found out the length of AM. AM, from the domain, it is very easy to see that AM equals to AB minus BM. That is to say, AM equals to AB, that is A, minus MB, that is R. So in conclusion, AM equals to minus R. Then found out the length of line segment NC. NC equals to BC minus BN. BC equals to B and BN equals to R, therefore NC will be equal to B minus R. Then I presented to you rule number 2 that the lengths of two tangents from a common external point to a circle are equal. So here we have, if we focus on the common external point A, we have two tangents to this circle, tangent AM and tangent AL. According to rule number 2, they are equal to each other. That is to say AM equals to AL. But we have already found out that AM equals to A minus R, and it is also equals to AL, according to rule number 2. Therefore, AL will be also equal to A minus R. Then we focus on the common external point C. According to rule number 2, we have two tangents to this circle, tangent CN and tangent CL. And according to rule number 2, they are equal to each other. That is to say, CN equals to CL according to rule number 2. But we have already found out that CN equals to B minus R, and it is also equals to CL. Therefore, CL must be also equal to B minus R. So, in the hypotenuse AC, so in conclusion, we found out that A equals to B minus R and LC equals to B minus R. And the hypotenuse AC equals to AL plus LC. The hypotenuse AC equals to AL plus LC. AM equals to A minus R, LC equals to B minus R, and AC equals to C according to the definition. So in conclusion, we found out that C equals to A minus R plus B minus R. That is to say, C equals to A plus B minus R is minus 2R. So C equals to A plus B minus 2R. So 2R, here we added 2R to this equation and found out that 2R plus C equals to A plus B. Here we subtracted C from this equation and found out that 2R equals to A plus B minus C. We divided this equation by 2 and found out that R equals to A plus B minus C over 2. Okay, so we found out the general formula for the radius of a circle that is inscribed by triangle ABC that could be any right triangle, and especially they could be those two specific right triangles. That is to say, we can use the new formula in order to find out the radius of those two circles that are inscribed by those two right triangles. So we have R equals to A plus B minus C over 2. That is to say, R equals to the sum of the perpendiculars minus the hypotenuse over 2. In the first right triangle, we have side AB equals to 8, side BC equals to 6, so it is 8 plus 6 minus the hypotenuse, that is 10 over 2. 8 plus 6 is 14, 14 minus 10 is 4, and 4 over 2 is 2. So here the radius of this circle that is described by this specific right triangle equals to 2 units. And we have also the second option. Here, according to this formula, here R equals to A plus B. A is 8, B is 15, minus C, that is the hypotenuse 17. So it is 8 plus 15, that is 23, minus 17, the hypotenuse 17, that is, so 23 minus 17 is 6, and 6 over 2 is 3. So in conclusion, we found out that there is two solutions to this question, and the radius of this circle that is described by the right triangle ABC could be equal to either 2 units or 3 units. So the answer to the question is that the radius of this circle that is described by the right triangle ABC could be equal to 2 units and 3 units. To 2 units or 3 units. We finished with the first question, then I presented to you the second question, and we solved the second question in 2 different methods. So in the drawing we have a quarter circle. A or B is a quarter circle. Side OB equals to 2 units. AD equals to DO. And we want to find out the area of the blue right triangle, triangle DCB. Okay, so here we know that AOB is a quarter circle, therefore point O is the center of the quarter circle, angle AOB equals to 90 degrees, and the radius of this quarter circle equals to OB, and it is also equals to AO, that is equal to 2 units. Then we defined AD is x, therefore DO must be also equal to x because they are equal to each other. So from the drawing it is very easy to see that DO plus AD, that is x plus x, equals to AO, and it is equal to OB, that is the radius of the circle, that is equal to 2 units according to what is given as the question. So here x plus x is 2x, and according to this normal equation, 2x equals to 2. We divided this equation by 2 and found out that x equals to 1 unit. Here, AD is equal to x equals to 1 unit, and DO that is also equals to x equals to 1 unit. Then we completed the quarter circle to a circle. Then here we extended the radius BO by straight line until it touches the circle at point P. So point O is the center, point P is the point on the circle itself. This is exactly the definition of a radius. So PO is the radius of this circle that is equal to 2 units. Okay? Then actually we extended the radius BO by straight line, so when you extend a straight line by straight line, the result is straight line. So the result that is BP, it is a straight line, and we have this straight line that passes through the center of the circle. Any straight line that passes through the center of the circle and touches the circle at 2 points is defined as a diameter. So PB is the diameter of this circle. Then we extended side CD by straight line, and we actually don't know until it touches the circle, and we don't know where it will touch the circle. So we assumed that the extended CD will touch the circle at point X. Okay, so actually we have here peripheral angle BCX that is equal to 90 degrees. Okay, we have peripheral angle BCX that is equal to 90 degrees. And this peripheral angle BCX, it doesn't rest on the diameter of the circle that is PB. And because of the fact that peripheral angle BCX is equal to 90 degrees and it doesn't rest on the diameter, it is a contradiction because any peripheral angle that is equal to 90 degrees must rest on the diameter. Okay? So we have a contradiction, and in order to solve the contradiction, we must conclude that point X merge with point P, and we have here peripheral angle BCP that is equal to 90 degrees, and this peripheral angle BCP indeed rests on the diameter. Okay, so actually we can conclude from it that when we extend side CD by straight line, it must touch the circle at point B and only at point P. Okay, that is to say, peripheral angle BCX equals to peripheral angle BCP because point X merges with point P. Okay, so we know that BP is the diameter of the circle, that is to say it is absolutely a straight line, and we know that the sum of the angles on one side of a straight line equals to 180 degrees. So if we focus on the upper side of the straight line, or on the upper side of the straight line BP at point O, then the sum of the angles must be equal to 180 degrees. So here we have 90 degrees plus the size of this angle, that is actually angle AOP, so that they must be equal to 180 degrees. So if we subtract 90 degrees from this equation, we get that the missing angle here must be equal to 90 degrees. So this angle equals to 90 degrees, therefore triangle DOP is the right triangle. So we can implement the Pythagoras theorem on the right triangle, triangle DOP. According to the Pythagoras theorem, PD square equals to DO square plus PO square. So PD square equals to DO square. DO is 1, so DO square is 1 square, that is 1, plus PO square. PO is 2, so PO square is 2 square, that is 4. So in conclusion, found out that PD square equals to 1 plus 4, that is 5. We took out of this equation and found out that PD equals to the square root of 5 units. Then we repeat it on the same process on the right triangle, triangle DOP. In this right triangle, according to the Pythagoras theorem, dB square equals to DO square plus OB square. So dB square equals to DO square. DO is 1, so DO square is 1 square, that is 1. Plus OB square. OB is 2, so OB square is 2 square, that is 4. So dB square equals to 1 plus 4, that is 5. We took out of this equation and found out that dB equals to square root of 5 units. Here dB equals to square root of 5 units. Then I presented to you rule number 1 and we implemented rule number 1 in our drawing. According to rule number 1, if we have this circle and we have chord AB that intersects with chord CD 8.0, again chord AB intersects with chord CD 8.0, then AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We can implement rule number 1 in our drawing, because in our drawing we have chord AZ that intersects with chord CP at point D. Again, chord AZ intersects with chord CP at point D. Therefore, according to rule number 1, we get that AD times DZ equals to CD times DP. Again, AD times DZ equals to CD times DP according to rule number 1. AD equals to 1, DZ equals to 1 plus 2, that is 3, times CD is the missing line segment, times DP. DP is square root of 5 units. So in conclusion, I found out that 3 equals to square root of 5 times CD. We divided this equation by square root of 5 and we found out here CD, the missing line segment, equals to 3 over square root of 5 units. Then we implemented the Pythagoras theorem on the right blue triangle, triangle DCB. According to the Pythagoras theorem on the right blue triangle, triangle DCB, dB square equals to CD square plus CB square. Again, in the right triangle, triangle DCB, dB square equals to CD square plus CB square. dB is equal to 5, so dB square is 5. That is equal to CD square. CD is 3 over square root of 5, so CD square is 9 over 5. Plus CB square is the missing sign, so we leave it as it is. So in conclusion, we found out that 5 equals to 9 fifths plus CB square. We subtracted 9 fifths from this equation and found out that CB square equals to 5 minus 9 fifths. Then we multiplied 5 by 5 and then we divided by 5 in order to have a common factor of this expression, and found out that CB square equals to 5 times 5 is 25 minus 9 over 5. 25 minus 9 is 16 over 5. So here CB square equals to 16 over 5. We took out of this equation and found out that CB equals to the square root of 16, that is 4 over square root of 5. So in conclusion, we found out that CB equals to 4 over square root of 5. Now it is very easy to find out the area of the blue right triangle. It is equal to the base of the triangle, that is DC, times the height to the base, that is CB over 2. Again, the area of the blue right triangle, triangle is DCB equals to the base, that is CD, times the height to the base, that is CB over 2. CD equals to 3 over square root of 5 units, times CB equals to 4 over square root of 5 units, all divided by 2. Here 3 times 4 is 12. So in the numerator we have only 12. In the denominator we have square root of 5 times square root of 5 is 5 times 2. Here 12 over 2 is 6, so in the numerator we left only with 6. And we have here square root of 5 times square root of 5, it is actually 5. Here it is square root of 5 times square root of 5, that is actually 5. All divided by 2. So we have 12 over 2 is 6, so in the numerator we have 6. In the denominator what is left is only 5. So in conclusion, the area of the blue right triangle, this blue right triangle, triangle DCB, equals to either 6 over 5 units, or in terms of numbers it is equal to 1.2 square units. Then I presented to you the second method to find out the area of the blue right triangle, triangle DCB. According to the second method, in the second method, we use the following things that we already found out in the first method. So here we already found out that AD equals to 1 unit. DO equals to 1 unit in the first method, and we completed the quarter circle to a semicircle. We already found out that this angle equals to 90 degrees, this angle also equals to 90 degrees according to the first method. Point O is the center of the circle, of the semicircle, point P is the point of the semicircle itself. This is exactly the definition of a radius, so PO is the radius of the semicircle, that is equal to 2 units. Okay, then we extended side CD by a straight line, and according to the method 1, the extended CD must touch the circle at point P, only at point P, only at point P. Okay, so we have here right triangle, triangle DOP. According to the first method, the hypotenuse DP equals to the square root of 5 units, and the hypotenuse DB of the right triangle DOB equals to also square root of 5 units. We defined angle DPO as theta. This angle equals to 90 degrees, so the missing angle must be equal to 90 degrees minus theta in order to complete the sum of the angles in the right triangle DPO to 180 degrees. This angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is 180 degrees. Likewise, in the right triangle BCB, this angle equals to theta, this angle equals to 90 degrees, so this angle must be equal to 90 degrees minus theta in order to complete the sum of the angles in this right triangle, triangle BCB to 180 degrees, this angle must be equal to 90 degrees minus theta. Then we proved that the right triangle PDO is similar to the right triangle BCB. Why those two right triangles are similar to each other? First of all, those two angles are equal to each other, they are both equal to 90 degrees, therefore they are equal to each other. Those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. And this angle is a common angle that belongs to both triangles, therefore this angle equals to itself. So we actually proved that the right triangle PDO is similar to the right triangle PCB according to angle similarity rule. Okay? And from the fact that the two right triangles are similar to each other, we will conclude that PD over PB equals to DO over CB, and it is also equals to PO over PC. I'll repeat again, PD over PB equals to DO over CB equals to PO over PC. PD equals to square root of 5 units. Here PB equals to 2 plus 2, that is 4. DO equals to 1, and CB is the missing line segment. Here PO equals to 2, and PC equals to square root of 5 plus DC. So in conclusion, found out that square root of 5 over 4 equals to 1 over CB equals to 2 over square root of 5 plus DC. We created the first equation from this long equation, square root of 5 over 4 equals to 1 over CB. We cross multiplied this equation and found out that CB times square root of 5 equals to 4. We divided this equation by 4, by square root of 5, and we found out that here CB equals to 4 over square root of 5. Then we implemented the Pythagoras theorem on the right broad triangle, triangle DCB. According to the Pythagoras theorem, dB square equals to CB square plus DC square. dB is square root of 5, so dB square is 5. CB is 4 over square root of 5, so CB square is 16 over 5 plus DC square, that is the missing side. Then we subtracted 16/5 from this equation and found out that 5 minus 16/5 equals to DC square. Here we multiplied 5 by 5 and then we divided by 5 in order to have a common factor of this expression. So 5 times 5 is 25, so it is 25 minus 16 over 5. 25 minus 16 is 9 over 5. So in conclusion, found out that DC square equals to 9 over 5. Then we took out of this equation and found out that DC equals to square root of 9 is 3 over square root of 5. So in conclusion, found out that DC equals to 3 over square root of 5. Now it is very easy to find out the area of the blue right triangle, triangle DCB. the area will be equal to the base of the triangle that is DC times the height of the base that is CB over 2. So the area of the right blue triangle DCB equals to the base of the triangle that is DC times the height of the base that is CB over 2. DC equals to 3 over square root of 5 units, CB equals to 4 over square root of 5 units, all divided by 2. In the numerator we have 3 times 4, that is 12. In the denominator we have square root of 5 times square root of 5, that is 5, times 2. Here 12 over 2 is 6, so in the numerator we left only with 6. In the denominator we left only with 5. So in conclusion, the area of the blue right triangle DCB will be equal to either 6 over 5 units, or in terms of numbers it is equal to 1.2 square units. Okay, so in both methods we arrive to the same result. Okay, thank you very much.